Imagine your most capable AI agent has painstakingly built up this accumulated context of, say, over 18,000 tokens.
Right, a massive playbook.
Exactly. It's navigating a really complex environment, it's making API calls, and consistently hitting a highly respectable, like 66% accuracy rate on a difficult benchmark.
Which is great for an agentic workflow.
It is. It has essentially learned the perfect, highly specialized playbook for the job. But then an automated optimizer decides to, help by compressing that memory into a more concise prompt.
Oh, no.
Yeah. In a single step, those 18,000 tokens are crushed down to just 122 tokens. And the agent's accuracy instantly plummets to 57%.
Which is an absolute tragedy. Because that compressed performance actually drops the model below its raw zero-shot baseline.
Right. It's worse than if it hadn't learned anything at all.
Exactly. The optimization process didn't just fail to improve the agent, it actively lobotomized the agent's baseline reasoning capabilities. I mean, it erased the very domain heuristics the agent needed to function.
Welcome to the deep dive. For those of you listening, the engineers, the data scientists, the mathematicians navigating the absolute bleeding edge of machine learning. That modifying a language model's behavior post-training is really migrating away from structural permanence.
Yeah, we are moving away from those massive surgical fine-tuning runs where knowledge gets baked directly into the model weights.
Simply because constantly updating parameters for every new edge case in an agentic workflow is computationally expensive and, frankly, notoriously opaque.
We have clearly entered the era of context adaptation. I mean, managing dynamic memory and optimizing system prompts at inference time is vastly faster.
But that transition introduces new breaking points, which brings us to the core mission of our analysis today. We are dissecting a fascinating new paper from researchers at Stanford, Samba Nova, and UC Berkeley.
And they propose a framework called Agentic Context Engineering, or ACE for short.
Right. And the central thesis of the ACE paper is a direct challenge to how we currently handle that inference time memory. The authors argue that while context adaptation is undeniably the future, our current state-of-the-art methods structurally fail when applied at scale in complex environments.
Yeah, they are basically arguing that context should never be treated as a static, concisely optimized prompt. It needs to be a comprehensive, continuously evolving playbook that literally grows from execution feedback.
To appreciate the architecture they propose, though, we have to look closely at the failure modes of our current natural language feedback optimizers.
Right. When we look at methods like GPA, which attempts to use gradient-based approaches to optimize prompts, or TextGrad, where text itself is treated as a backpropagated gradient, they both hit two catastrophic bottlenecks in multi-step agentic loops.
And the first bottleneck is what the authors identify as the brevity bias.
Yeah.
Wait, I actually need to stop you there and push back on that premise a bit.
Sure, go ahead.
In almost every other area of machine learning, compression and brevity are exactly what we want. We want the model to generalize. I mean, we use regularization techniques specifically to panelize overly complex models so they don't overfit to localized noise.
Right, L1, L2 regularization, sure.
Yeah.
Yeah.
So why is brevity suddenly being labeled as a catastrophic bottleneck when we were talking about prompt optimization?
It's a totally valid instinctual generalization, but think about the domain application here. Brevity bias in this context is like asking an expert mechanic to write down the exact diagnostic step for fixing a highly specific rare engine timing issue.
Okay.
And then the automated optimizer summarizes those complex instructions into basically use a wrench and check the engine.
Ah, so it's technically true, but useless.
Exactly. The summary is broadly true, and it is highly compressed, but it deletes the precise, localized heuristic the mechanic actually needed to solve the problem. Current optimizers algorithmically force instructions into the most concise, generalized prompts possible.
I see the distinction. When you force an LLM to penalize verbosity in its prompt, it strips away the highly specific edge case handling.
Precise.
If an agent is navigating a specialized database, a generalized prompt might say, always verify your filtering criteria, but the empirical heuristic the agent actually discovered during a failed run might be, always resolve identities from the user app database using proper date-time range comparisons instead of string matching.
Yes, exactly.
The brevity bias actively deletes that necessary technical nuance in favor of sounding concise.
Which leads directly to the second, even more destructive bottleneck. The lobotomy scenario you introduced at the start of our deep dive, the authors call this context collapse.
Let's unpack the mechanics of that collapse. Current optimization methods rely on a language model to monolithically rewrite an entire memory or prompt in a single autoregressive pass.
And autoregressive models fundamentally struggle with maintaining the fidelity of massive accumulated knowledge during a single generation loop.
Because they're predicting the next token based on learned distributions.
Exactly. When you ask a model to ingest a massive context and output a revised version of that entire context, the model defaults to its training priors. And those priors strongly favor summarization. The fidelity abruptly erodes.
The empirical evidence the authors provide is striking. We mentioned the 18,000 tokens dropping to 122. That case study was run on the AppWorld benchmark.
Right, which is brutal.
For context, AppWorld is an intensely complex evaluation suite that tests an agent's ability to use APIs, write Python code, and interact with a simulated environment to achieve multi-step goals. It is not a toy benchmark. It requires managing complex JSON payloads and rigorous logic.
And when the JIPA optimizer triggered a monolithic rewrite of the agent's memory bank on that benchmark, the context collapse wasn't just a minor degradation. It was an abrupt erasure of the specific API parameters and troubleshooting rules the agent had learned over dozens of rollouts.
So monolithic rewriting is a dead end for scalable agentic memory.
Completely. The authors realized that relying on a single neural forward pass to evaluate an error, summarize a lesson, and restructure the entire prompt was overloading the model's cognitive capacity.
They realized that true context engineering requires a strict multi-agent division of labor.
Which is the theoretical foundation of the ACE framework. It introduces a modular tri-node system consisting of a generator, a reflector, and a curator.
And for the sake of rigorous evaluation, the authors used the exact same underlying open source model, DeepSeek v3.1, for all three roles, right?
Yeah, and that is a crucial methodological choice. It prevents any hidden information leakage that would inevitably occur if they used, say, a massive proprietary model to subtly guide a smaller open source model.
Let's examine the specific responsibilities of these nodes. The generator is your frontline worker.
Right.
It produces the reasoning trajectories and actively executes code in the environment. It is the agent actually making the API calls, reading the error tracebacks, and surfacing the successful strategies alongside the recurring pitfalls.
And once a trajectory is complete, the reflector takes over. The reflector's entire purpose is to separate the evaluation phase from the curation phase.
Just basically the critic.
Exactly. It ingests the generator's execution trace and analyzes it against the environmental feedback. If the system is operating in an offline training environment, it can even compare the trace against a known ground truth.
Got it.
The reflector diagnoses the exact logical gap between what the generator attempted and what the environment demanded, and it extracts concrete, highly isolated lessons.
That separation of concerns is a brilliant structural pivot, because then you have the curator.
Yes.
The curator takes those isolated, granular insights from the reflector and integrates them into the evolving playbook. The elegance here is that by decoupling the reflector from the curator, you separate the extraction of the insight from the actual structural updating of the prompt.
Just consider the alternative. If you ask a single LLM to look at a failed Python script, figure out why the API rejected the payload, and then rewrite a 20,000 token system prompt to include that lesson.
The model just gets overwhelmed.
Exactly. It defaults to the brevity bias. By isolating the curator, its only mandate is to integrate a specific, detailed lesson without altering the rest of the established playbook.
But wait, that introduces a massive technical hurdle. We have established these three agents, but how does the curator actually modify the context without triggering the catastrophic context collapse we just spent 10 minutes dissecting?
That's the million-dollar question.
If we are entirely abandoning the monolithic prompt, what is the actual data structure of this memory?
The authors solve this by abandoning continuous text entirely in favor of incremental delta updates. ACE represents the context as a collection of structured, itemized bullets.
Oh, interesting.
Yeah, it looks much more like a highly organized database of memory entries than a traditional system prompt. Each individual bullet contains strict metadata, like a unique identifier, success and failure counters, and the specific content itself.
So the content might be an API schema, a code template, or a highly specific troubleshooting heuristic. I see where this is going. Instead of generating a new rewritten document, the curator simply produces a delta context, a tiny set of candidate bullets containing the new insights.
And here's the critical engineering breakthrough. Those deltas are merged into the master playbook deterministically, using lightweight, non-LLM logic.
Wait, they're using basic Python logic instead of an LLM for the merge.
Yes, you are not asking a neural network to append the text and hoping it doesn't hallucinate or summarize. You are using deterministic code to insert the new structured bullets into the list.
That's incredibly efficient.
It is. This localized editing enables parallel batching of adaptation. You can literally have 50 different reflector curator loops running on 50 different execution traces simultaneously and merge all their specific deltas into the master playbook at the exact same time without conflicts.
So you are substituting a stochastic, computationally expensive LLM generation step with basic deterministic code. That fundamentally solves the context collapse.
It does.
But it raises a new issue. If you are constantly merging new bullets, how do you prevent the playbook from turning into an unreadable, redundant mess?
That is managed through what the paper calls a grow and refine mechanism. The context isn't just an infinitely extending text file. As new items are appended, existing items have their usage counters updated.
Oh, I see.
Yeah. If the generator successfully uses a specific code template, that bullet's success counter increments. If a heuristic leads to an API error, its failure counter increments.
And what about redundancy? I mean, if 50 concurrent loops discover the exact same API quirk, you don't want 50 identical bullets in your playbook.
The system uses semantic embeddings to compare the bullets. When the curator proposes a new bullet, the system computes its embedding vector and runs a cosine similarity check against the existing bullets in the playbook.
Oh, so if they map too closely in the vector space.
Right. If the semantic similarity crosses a certain threshold, the system recognizes it as a duplicate. Instead of adding the new bullet, it simply updates the counter on the existing semantically identical bullet.
Which gives machine learning engineers an incredible amount of architectural flexibility. You could implement proactive refinement, where you run that embedding deduplication after every single delta update.
Yep.
Or if compute is tight, you can use lazy refinement. You let the playbook grow unstructured for a while and only run the embedding deduplication when you start approaching your model's maximum context window limit. You gain fine-grained control over your compute versus accuracy trade-off.
The underlying logic of the architecture is deeply sound. But as any seasoned practitioner knows, theoretical elegance frequently falls apart in messy, real-world evaluations.
True.
The ultimate question is whether an uncompressed, highly detailed, procedurally merged playbook actually outperforms an optimized, concise prompt in complex multi-step scenarios.
Let's dive into those empirical results then. On the App World benchmark, ACE achieved an average performance gain of 10.6% over strong baselines. But the metric that truly stands out is how it performed in the online adaptation setting.
The online setting is the ultimate test of a self-improving agent. In this scenario, the agent has zero access to ground truth labels. It cannot look up the correct answer.
Right, no cheat codes.
Exactly. It must rely entirely on environmental execution feedback, for instance, analyzing whether an API call returned an error traceback or a valid JSON payload. Relying solely on that environmental signal, ACE improved by 14.8% over the standard React baseline.
Wow. And for those familiar, React is the standard reasoning and acting loop that most agents use to interact with tools. Beating it by nearly 15% without ground truth is a massive leap.
But here is the milestone from the sources that completely changes the deployment calculus. On the public App World leaderboard, using the open-source DeepSeek v3.1 model, the ACE architecture matched the top-ranked production-level IBM CUGA agent on average.
And to put that in perspective for you listening, IBM CUGA is powered by GPT 4.1. ACE actually surpassed the GPT 4.1 agent by 8.4% in task goal completion on the significantly harder test challenge split.
Let's examine why that happened. Because it wasn't just raw model capability. GPT 4.1 is an immensely powerful model, but the IBM agent was constrained by static or monolithic context handling.
Right.
When the environment presented complex, highly specific edge cases in the test challenge split, the GPT 4.1 agent didn't have the granular, dynamically evolved heuristics required to navigate them.
It had a generalized summary instead of the exact playbook.
Exactly. The DeepSeek model, despite being smaller and open source, had an exhaustive, uncompressed playbook of specific API rules it had learned. It proves that a sophisticated memory architecture can allow a smaller, open-weight model to punch far above its weight class and defeat massive proprietary systems.
And we see this exact dynamic repeated in domain-specific reasoning benchmarks as well, right?
Yes, the authors deliberately pivoted away from general coding tasks to test the framework on the financial domain, specifically using the Finare and Formula benchmarks. These tasks require processing complex XBRL financial documents, identifying tags, and applying strict accounting logic.
And financial regulations are the ultimate test case for why you cannot compress heuristics. An accounting rule isn't something you can, algorithmically summarize. It is either applied perfectly or it is a compliance violation.
Precisely. On these financial benchmarks, ACE delivered an 8.6% average performance gain over state-of-the-art baselines like GPR and Improv 2.
Oh, MI-Prova 2 is an advanced prompt optimization framework.
It is, but again, it falls victim to compression. The evolving playbook of ACE retained the exact uncompromised financial rules required to process the XBRL documents. The optimizer summarized those rules into uselessness.
Now, we need to remain rigorous here and proactively highlight a significant caveat mentioned in the paper. The ACE framework is not magic. It is entirely bottlenecked by the quality of the execution feedback.
Yeah, that's a crucial point.
If you deploy this agent in an environment where the signals are opaque or useless, imagine an API that simply returns a silent error 500 with no diagnostic traceback. The reflector has no valid signal to analyze.
It is a critical constraint. The system is fundamentally an empiricist. It learns entirely from interaction. If the environment yields no granular data, the reflector might begin to hallucinate reasons for the failure.
And then the curator integrates those hallucinations.
Right. The curator will integrate those spurious lessons, and the playbook will actually degrade over time. The framework requires environments that provide rich, descriptive feedback.
That makes total sense. Garbage in, garbage out applies to environmental feedback just as much as training data. Now, I want to address the immediate practical pushback that any systems engineer listening is already calculating.
The token costs.
Exactly. We are talking about intentionally abandoning prompt compression. We are advocating for growing massive, highly detailed 20,000 token context playbooks. Doesn't this approach cause inference latency and token costs to absolutely skyrocket?
It is the most logical concern, but the paper details an efficiency paradox that is highly counterintuitive. ACE actually reduces adaptation latency by 86.9% compared to GPA on the AppWorld benchmark. Furthermore, it requires 75.1% fewer rollouts to achieve higher accuracy.
Walk me through the math on that. How do you slash latency by nearly 87% when your context window is vastly larger?
It all comes back to the delta updates. With monolithic optimization methods, the LLM is forced into massive generation loops. Every time you need to update the prompt, you are asking the LLM to generate thousands of tokens to rewrite the memory.
And output token generation is the most computationally expensive and time-consuming part of running an LLM.
Exactly. With ACE, the LLM is only generating the tiny isolated delta bullet, maybe 50 or 100 tokens. The actual merging of that bullet into the 20,000 token playbook is handled by basic Python code.
So you completely bypass the massive token generation costs associated with monolithic rewriting.
Precisely. The authors noted that on the finer benchmark, this delta approach reduced token dollar costs by 83.6%.
I understand the savings on the generation side. You are outputting fewer tokens. But what about the ingestion side? You still have to feed a 20,000 token playbook into the generator's context window for every single user query.
This is where we have to look at modern serving infrastructure. The authors emphasize that large input contexts are no longer the linear bottlenecks they were even 12 months ago. We now have highly optimized systems for managing context specifically, KV cache reuse, and KV cache compression algorithms like Chen, alongside dynamic offloading.
Let's briefly explain the attention mechanism math there for context. Because the playbook is structured as discrete bullets and remains static between the delta updates, you do not need to recompute the attention over the entire document for every single query. You compute the key value cache for the playbook once. You hold those computed activations in memory. When a new user query comes in, the model only computes the attention mechanism for the new query tokens and the newly generated response tokens while simply referencing the cached playbook.
Exactly. You amortize the computational cost of that massive context over hundreds or thousands of queries. The system's infrastructure has evolved to support exactly this kind of extended static memory architecture. The cost of a large prompt is no longer the limiting factor. The limiting factor is the generation cost of updating it, which ACE solves.
Synthesizing everything we have covered, what is the core architectural takeaway for our listeners as they design the next generation of agentic systems?
The fundamental paradigm shift is that for expert domains and multi-step agentic workflows, language models do not need compressed summaries. They need comprehensive, structured, continuously evolving playbooks. By modularizing the architecture into generation, reflection, and curation, ACE solves the structural flaw of context collapse.
It preserves those granular heuristics.
Yes, it preserves the granular, localized heuristics that actually solve hard engineering problems. Most importantly, it empirically proves that with a sophisticated memory architecture, smaller open-weight models can match or exceed the performance of massive proprietary models that are still shackled to static prompts.
It really changes how we view the relationship between the computational engine of the model and its memory. And that leads me to a final, highly provocative theoretical implication from the discussion section of the source paper. We started this deep dive by comparing fine-tuning to surgery, baking knowledge permanently into the neural weights of a model. But what happens when that baked-in knowledge becomes a legal or operational liability?
You're talking about the problem of machine unlearning.
Exactly. Think about strict privacy compliance, like the GDPR right to erasure. If an LLM has internalized a user's private data, or perhaps a flawed, biased financial heuristic into its trillions of parameter weights, extracting that specific piece of knowledge is a mathematical nightmare.
Oh, it's virtually impossible. You often have to retrain the model entirely from scratch, or apply highly unstable, unlearning algorithms that can inadvertently damage the model's core capabilities.
It is arguably one of the hardest open problems in deep learning right now, because weights are fundamentally opaque and entangled. But look at the architecture of ACE. Because ACE relies on human interpretable modular context bullets rather than opaque weight updates, it opens a highly practical, immediate avenue for machine unlearning.
That's a fascinating point.
If a specific operational heuristic becomes outdated, or if a piece of stored data is suddenly flagged as violating a new compliance regulation, a data engineer does not need to touch the model weights. They do not need to run a gradient descent algorithm. You simply query the playbook, identify the specific bullet ID containing the flagged data, and delete it.
The change is deterministic, it is immediately verifiable for compliance audits, and it takes milliseconds. You are replacing a complex, mathematically entangled calculus problem with a simple database query.
It transforms AI safety and compliance from an algorithmic nightmare into a standard database management task. So, I want to leave you with this thought to mull over as you build. As we move toward highly capable, continuously learning AI systems, maybe the future of safe ML adaptation doesn't lie in the endless, messy surgery of weight fine-tuning. Maybe true scalability lies in the sophisticated engineering of a language model's dynamic, structured, and entirely cacheable memory.